Hello, everybody. I am Krishna Kumar. I work as a group engineering manager at Microsoft, working on PostgreSQL open source as well as the managed service side of things. Today, I bring to you a talk called PostgreSQL and Linux Kernel Interactions. In this, you will learn a lot about the internals of how Postgres interacts with the Linux kernel and how to look at this, how to debug this, and a lot more. Welcome and come watch my talk. Thank you. Cool. Let's get started. Before we go into details of the presentation, let me give a little more detailed intro of myself. As we just talked about, I'm engineering manager for Postgres engine in at Microsoft. I started my career a couple of decades back, porting Linux to custom MIPS and SH4 boards, as well as writing kernel device drivers. From there, after learning about embedded systems, I moved on to HPC and parallel file systems and more of these deeper storage related areas. Uh, then I joined a startup called StoreSimple, which got acquired by Microsoft, and then thereby joined Microsoft. In Microsoft, I worked a while in StoreSimple area, then moved to Kubernetes, then moved to databases space. I have been working in Postgres space for some time now, both on the open source side of the space as well as the managed service side of Microsoft. Then one of the top like top things that happens during my day to day interactions is that I get to interact a lot with Postgres experts, and that gives me an opportunity to learn a lot more internals. And I'm fortunate to have such people in the group as well as people in the community from whom I learn a lot. This talk is primarily based on lessons learned from such interactions, as well as a lot of homework and a lot of issues that I have tried debugging in the past as well. Cool. So we'll go look at what are the various areas that we'll cover in this talk. What are you going to really learn in this, right? That we'll talk about that a bit. So first thing is that we will look at this tool called Strace, which is usually used for debugging purposes. Here we are using this as an educational tool as well. Strace will give you indicator of how what kind of system calls are Postgres really calling, and also will give you where it's waiting, where the cumulative summary of it, and details related to it. So typically you would use this as a debugging tool, but in this case we'll use as more educational purpose again. From here we will move to like the overview of how Postgres interacts with the Linux kernel. So just so that you know, like the title does say it, but just I would like to repeat this, that we will be talking more about Linux kernel interactions in this case. Postgres runs on many other platforms, and there are internals to learn there as well. But for interest of time, we'll just focus on Linux side of things. From the kernel interaction overview, we will move to typical system calls with Postgres would make in general. What are the areas that we would cover, as well as that Postgres common calls occur. So primarily, we would then shift to how process management is done within Postgres by the help of these system calls from the Linux kernel. From there, we will look at memory related system calls, signals, and then we will go and dig deeper into some of the areas of file management. Basically, uh, in file management, we'll dig deeper into the read side of things, buffered IO and direct IO. And also we'll talk about the recent features which has been added into the into Postgres, primarily in areas where Postgres interacts with the kernel side of things. We'll then quickly switch to exploring how prefetching is done in Postgres using these kernel mechanisms. Then we look at other system calls which are used. Then also cover some of the newer, like PG17 and Postgres like 18 newer usages of some of these calls. And from there, we'll conclude our talk. Cool. So let's move. So Strace is a very uh, useful tool in many scenarios. These are used to debug issues. In this case, we'll use it for learning how system calls are made. Uh, Here is a screenshot of an strace command. Strace has the ability to attach to a running process. In this case, we are using the PID of the process using -p to attach to it. We are using this flag in strace, which will make sure that even if the process forks, it still can follow the child and then also account for the calls which are made from the child as well. So those are the -f and -p flags. -c would give you a cumulative summary of how the usage of system calls were happened while running the session. So in this screenshot, I ran it for a while and then did Control C to stop it. As you can see, the summary of the system calls that were made. Some of them were a lot of opens were made, or a lot of closures, and then there were like fsyncs and writes and a bunch of these things. A bunch of the system calls were made. So this shows you the summary of the calls, but typically you would use this to debug scenarios where, let's say, you find a process which is hanging and it's not moving forward. Then you can attach using a trace and figure out which call it's hanging, and then reverse understand what's going on, and from there figure out the root causes of issues. Here we'll continue to use a trace in the next set of like next portions of the slides as well. At a high level, Postgres interacts with the kernel via the libc calls, which is interesting because when you run a trace, what you would see is the system calls, and when you look at Postgres, you would see the glibc usage in the code. So a lot of times, what happens is that libc abstracts out the complexities that are there from the system calls, right? Like you don't have to hand code the system call a number and like wrap it around and various other uh, like complex scenarios that you have to take care. You can just make some calls and things will start working. For example, for fork, the call of fork would actually end up with a system call of clone with a bunch of flags that needs to be passed around. And libc will give you an abstraction which you can directly use, and it would end up in a clone call. P-read is another place where when you look at the calls that are made, you'll see the p-read, but the p-read would translate to p-read 64 in the platform that you're corresponding. If you're using 64-bit platform, that's where you would end up. That's what you would end up seeing in the S-trace. Malloc is another example where eventual system call is this break. Then there are a bunch of layers which we go through to before we get to the BRK system call. And once again, glibc comes to your rescue and makes it all a lot more simplified than what actually it has to do. The takeaway here is that Postgres interacts with the kernel via glibc calls, and there is a lot of simplification and abstraction that gets done, believe me, making somebody coding in Postgres their life easier when they interact with the kernel. Um, Cool. So next we will look at the examples of some of the areas that Postgres makes system calls. Uh, I have just listed some of the top areas. Like process management is definitely an area where Postgres uses a lot of system calls. Postgres currently is a process-based system, so as you can imagine, it needs to start a new process. It needs to get the PID of the process. It needs to exec some other process. Like there's a bunch of these interactions that it has to do with respect to process management, and a lot of these system calls are used in the way of making such operations happen. Memory is another area where we do have local memory for a given process, and also we have shared memory which is shared across processes. For both of these scenarios, there are a bunch of system calls like brk, mmap that we would use in order to make this happen. And again, like this goes through libc, but it's good to understand, learn, and kind of like have a picture around how these operations happen. Another area where Postgres uses system call is the signal area. There are many examples of signals getting used because it's again like process-based architecture. So stopping a process by using sigterm, like killing a process using sigint, and a bunch of these operations that needs to happen between two processes do happen via signals. So not just the user interactions, but also between processes, the interactions happen via signals. The next set of things that happen is like file interactions. So lot of Postgres operations are file based, as in both the the wall, the write ahead log, as well as the pages that are corresponding to the database are all stored eventually as files. Because of this, you need to open the file, close, read, write, sync, and a bunch of operations that you have to do. All of this again translates back to uh, calling system call via glibc, but file based system calls. Then as Postgres allows networking connections, you need to have network system calls as well, like listen and socket and accept, and a bunch of these calls that you need to do as well. Those all happen via help from kernel and Postgres maintenance. There is a category of calls that Postgres makes, which is called VDSO. It's called a virtual dynamic shared object thing, wherein every process in Linux would get this object. It will look like a system call, but it's a faster way to access some of the commonly and frequently used system calls. For example, getting the time is like a frequent part of dealing with the programming side of things. So VDSO provides you an easy way to do this, where you necessarily don't transfer into the kernel side of things, but at user land itself, you can get access to some of these updated variables which kernel keeps make sure to update. And we are not going to go into details of this in this particular talk, but in general it's good to be aware that there are these category which is looks like system calls, but like somewhere in the middle, hybrid form of this is what you would get on regular Linux process. Now let's let's go deeper. So first, let's look at the process management side of things. Here in the example, the first screenshot on the top right, what you see is that the postmaster comes up as a main process. Then it is spinning off its children like checkpointer, background writer, wall writer, and so on. All of that it uses this system call called clone. On the bottom, what you see is basically an Strace station which is run to trace out what kind of system calls happen. As you can see by the red marked areas, the PIDs which are all generated newly from the postmaster are all done using the clone system call. So every time Postgres starts off with the postmaster coming online, then subsequent children are spun off from it using the clone call. And also at the end of the day, those children also eventually end up calling some of the other processes. Like for example, here the archive call, which is like the process 23678, actually calls in another process whenever the archival has to happen. So that's why you see another clone, which is a slightly different variant of the clone system call, and then a separate PID is spun off from it to actually do the archiving part of it. So as long as Postgres remains to be process-based architecture, it will continue to use a lot of these process-based, process management-related system calls. That's kind of the takeaway from this slide. Let's look quickly at the memory related system calls. First thing to go back and remember is that we are in a process based architecture. So there are many mechanisms that Postgres employs to have processes talk to each other. Some of it is via the memory, and shared memory is a big part of how Postgres is architected. The technique generally, which starts off with in case of a static scenario, is that Postmaster would allocate some shared memory using the mmap call with anonymous backing, and then with the right flags, like in this case map shared, and then it would allocate this memory. Whenever our child process spins off from this Postmaster, it would actually get access to the shared memory, and then that shared memory is used as a common area where uh, processes can talk to each other and kind of uh, make the conversation for the life cycle of Postgres to continue. For the local allocations, like the BRK regular malloc functionality happens. For the shared thing, the nmap gets used, and in regular cases also nmap gets used a lot. So one system call or one takeaway from this slide, it is to remember that in case of memory and shared, and even in some local scenarios, nmap is the system call that would eventually get called into when Postgres operates over the memory. Cool. So the another area which needs a little bit of attention is the signals side of things. Postgres uses signals in various scenarios, both when it is taking in a user input, right? A user wants to tell Postgres processes to do something like, hey, sigterm or sigint, or sig user, or some other communication between the user and the process. Also, there are scenarios where Postgres uses it for its regular operations. And here is an example where that happens, where let's say the Postgres postmaster has some operation going on, and the background worker needs to come in and talk to the operation, and it's trying to synchronize certain operations. So in some scenarios, there is this concept of latch, which is used in many scenarios actually in Postgres. There is the concept of waiting on a latch and setting the latch where we are operating on this common space. So in case of waiting on a latch, it would use a combination of epoll, which is yet again a kernel facility which is available, and then the whole aspect of epoll and polling on a signal fd kind of scenario, which is like file descriptors where you can wait on. Conceptually, that's the thing. Like you have a set of file descriptors and wait on the file descriptors, and somebody who's now used the common resource that Latch is waiting on and wants to tell the other waiting processes that, hey, I'm done with it. Please go ahead and you start trying to access the resource. At that point, the set latch would send the SIGURG signal to indicate that the process is now able to free up this resource from what it was doing, and then the waiting process can try to acquire the resource and do the operation. So the concept that needs to be taken away, or like can be taken away from here, is that Postgres uses Signal a lot in many scenarios, like for user scenarios as well as for internal operations. And a typical scenario of like wait latch, set latch is an example where this gets used. But gets used as a tool of interprocess communication a lot across Postgres code. Uh, that's the that's the point we can note from here. Now, let's talk a bit about read side of things. As I was explaining in the earlier slide, Postgres operates on files both for the write-ahead logs as well as for the database pages. They're all files on the file system. So at some point in time, whenever Postgres has to read some data from these files, it uses the regular read system call. It's like pread eventually, right? Like the translation is like pread 64 eventually, where it will read from the disk. But the thing to remember is that kernel plays a big role in this, that when we are just doing a pread, it's like a buffered read, where every page that would be read generally is like cached in the kernel's page cache as well. And then when Postgres tries to access it, it's also available in the buffer. It's also brought onto the buffer pool. So the concept of double buffering is comes into picture here, where whenever Postgres tries to access some data from the disk, it will actually be accessing the copy of this from the page cache, and kernel will maintain this page cache in its using its own algorithms and its own mechanisms to make sure that Postgres doesn't incur the overhead when it tries to read it next. But at the same time, it also incurs this overhead that it also buffers itself, right? So Postgres is an area where it keeps these buffers, right, like the buffer pool, and it has a shared area where it keeps it. In case of wall, there's a wall buffer as well, but there is already extra memory used in kernel to buffer it. But in totality, this mechanism works well because the sophisticated algorithms that are used in the kernel page cache buffering would help Postgres from a lot of performance issues. So it does help, but uh, note that there is like double buffering happening in this case. So that's the summary of this slide. Let's look quickly at what direct IO would mean in Postgres world. So back in Postgres 17 and like around 17, we have this facility where you can enable direct IO now as a debug option. Uh, the whole thing is not yet fully wired, so it's requested to use in a developer debug mode. The screenshot that is shown in this picture shows how the the signal the buffer is like read in. Here on the left side, there is a table which is read. Like, note that this experiment was done like freshly. So then, when the table is read, you'll find that the third command here would actually indicate that the table read is buffered in the page like buffer pool of the Postgres, and at the end, the fincore command is run. This command will show you if there are pages from a given file which is kind of cached in the buffer cache, like the page cache of the kernel. So as you can see on the left, there is an 8K page which is like buffered in the page cache of the kernel run by fincore. And this is the typical operation, right? Like normal operation where direct IO is not enabled and you have like double buffering going on. On the right, what you see is that we are now enabling the direct IO just for testing purposes. And then we do the same operation freshly. The copy is made in the buffer pool. But then when we look at the fincore operations, we don't find any contents there, right? So that's where the difference between a direct IO and um, buffered IO would come into picture, where the kernel no longer buffers these pages. At some point in time, we would expect that Postgres would have direct IO and would gain all the associated performance benefits from it as well. Um, there is another quick concept that I wanted to bring to your attention. That is like in Postgres 17, there is this functionality which was brought in where um, there typically Postgres would read 8K pages like periods would happen. Here on the right side screenshot, you can see several 8K reads has happening for accessing a table. Whereas in 17, what you would see is that a single period with like a vectored read would happen. What that means is that if Postgres figures out that there is a combining that's possible, it would convert this to one call, thereby reducing the translation cost to the kernel by just single call. Prefetching is another scenario where a lot of these kernel optimizations can be used, wherein in 16, like Postgres 16, 17 kind of scenarios, where F advice is one of the call that can be made, where you can tell the kernel that, hey, I will need these areas of memory be read in advance. So which is like basically telling it to prefetch them, and then as Postgres gets to the point where it is really accessing it, it's already present in the kernel buffers. What that will bring is a lot of optimization, because as Postgres process to its whatever it was doing, for example, let's say it was doing a recovery and is trying to read each of the records and try to replay. By the time it reaches the right record, all of these backing pages of the both the wall as well as the pages would be there in kernel buffer, and the performance would be less performance would be penalty would be incurred with this. Another area where a lot of system call is used is like fallocate, where whenever a relation has to be extended, you typically end up using this fallocate system call, where there's no IO needed. It's like telling the kernel that, hey, extend the area, and then that single operation can bring you that. Another area is like seeking, where Postgres needs to know about the file size, and typically getting the file size information is a like overhead operation. So we would do like an lseek and then like figure out where the end of it, and that is used as the size of it. There's a lot of patches which is being worked on, where eventually these things will get cached and they will not be needing to do a lot of lcs, but typically you would find this in Postgres operations in uh, all recent versions as well. Sync file range is another space where whenever checkpointer has to do write back, it will do only specific ranges of write back, which would make sure that the IO workload is kind of like spread, and the the uh, whole write back is controlled in a way that there is not too many overloads at single point in time. So that's another thing to keep in mind while looking at some of these things on Postgres. Another fairly newer usages like copy file range is a space where there's a lot of usage that is coming through, where in the incremental backup restore, we use the copy file range and then create a database from template, which will come in Postgres 18. Also, we use copy file range, where you really don't have to do the copy inside from the kernel to user land and then copy it back. Instead, you just say this and kernel will just do this between the files. So that's another newer form of usages. I mean, the system and infrastructure existed, but Postgres is now using this a lot more. Big area of usage is the IO urine, which in Postgres 18, one of the most exciting features that is coming is that AO will be present now in most of the critical read paths. Here, the kernel facility of IO urine is what Postgres would Postgres can use, and that brings the async IO into the Postgres world as well. So these are fairly newer uses of it. There are many more usages of this getting planned as the modernization process of Postgres goes in. So that's the take of this thing. Cool. So we have come to the end of this presentation, this talk. I just wanted to say thank you to a lot of folks within the PostgreSQL committers and contributors team at Microsoft. Thank you, Thomas, Anders, Amit, Daniel, and Teresa for helping with this presentation, and in general, the community for being such open and collaborative environment where uh, a lot of things can be done in Postgres as well as people can come and learn. Hope you had a wonderful time. To get in touch with me if you want to learn more about more kernel interactions of Postgres. And thank you for attending this session. Thank you.